Okay, so now we're going to talk about the solutions to the problems for 4.8, which is the acid base. So if this is a weak acid, its conjugate base is this once it's lost the proton, so its conjugate base is simply going to be that azide ion, the N3 minus ion. When we write a net ionic equation for the acid-base reaction between hydroazoic acid and sodium hydroxide, so we need to remember that when we write a net ionic equation, if we have a weak acid, we do not write it dissociated. So we're going to write this as HN3 in solution, plus, now we do have a strong base, sodium hydroxide, so we're just going to write the hydroxide ion, AQ, yields, and now the hydrogen is going to come together with the hydroxide to give us water, and we're going to have that azide ion floating around in solution. Okay, when we talk about conjugate acid-base pairs, the only difference between a conjugate acid and its base is one hydrogen ion. So if we look at this, the sulfuric acid is not the conjugate acid of the sulfate ion because there's two hydrogens difference. So the conjugate acid of the sulfate ion would be HSO4 minus, not H2SO4. And so here we have just completely different species, so that can't possibly be the conjugate acid-base pair. And again, the difference between the hydronium ion and the hydroxide ion is two hydrogens, not one, so that's not a conjugate acid-base pair. So we would look at the hydrogen sulfate ion and the sulfate ion. This is an acid, this is its conjugate base because they differ only by one proton. Okay, in this diagram we need to identify and label two conjugate acid-base pairs. So the first thing I'm going to do is I'm going to look and see if I can find two species that differ only by a hydrogen. And since we have this little descriptor that tells us that this is water, that tells me that these little clear circles are hydrogen. So here I have water, and here I have water with one more hydrogen. So that tells me that the water and the hydronium ion are a pair because they differ only by one hydrogen ion. So there's one conjugate acid-base pair, and we'll come back and label those in a second. Now if we look at this and this, we can see again that they differ only by one hydrogen ion. So we're going to write this guy, whatever it might be. This is an acid of some sort because it has a hydrogen ion, and this is its conjugate base. So this is the acid. This is its conjugate base. This water is a base, and this is its conjugate acid. Had you initially picked this as an acid and this as a conjugate base, then that would be fine. This would just be your base, and this would be your conjugate acid. Because we don't know what the products and what the reactants are, as long as you have them paired up appropriately, it's fine. But you do need to have one base and one conjugate acid and one conjugate base. Now it's deliberately telling us that there's an acid here, and it's asking us, is this acid a strong acid or a weak acid? Well, we know that a strong acid is one that dissociates completely. And if we look at this diagram, we can see that we have acid molecules still put together. Then here's one that's dissociated and has donated a hydrogen ion to this hydronium molecule, maybe. We have lots and lots of acids that are still put together. So we're going to say that this is a weak acid because it's only partially dissociated. Okay, we're almost to the end. If the reaction shown below favors the formation of reactants, which is the strongest acid in the reaction. Well, we know that the forward reaction is only favored if it makes weaker acids and bases than it started with. So that tells me that this is an acid. I know that this is an acid. I know that this must therefore be its conjugate base. That means that this is a base and this is its conjugate acid. But in order for this reaction to go forward, this acid must be stronger than this acid. And so we can say that the hydrocyanic acid is the strongest acid in the reaction. By the same token, carbonic acid is a weaker acid than sulfurous acid, so it says which of the following reactions is more favorable, meaning more likely to happen. So, are we more likely to make carbonic acid, or are we more likely to make sulfurous acid? Well, sulfurous acid is a stronger acid, so we're more likely to make carbonic acid because it makes a weaker acid. Okay, so that is it for today's practice problems. As always, if you have any questions, let me know.